We have 4 presentations, including a brief one by me and 3 more by staff and students here, all on the same topic. And that topic is the electrification of large existing buildings. We'll be kind of sharing results, including case studies, a new web tool, and a new electrification map showing electrification retrofit projects all around the nation. We'll be sharing lots of resources here. Those will be available at a QR code at the end of the presentation. So all of those links will be there at the very end. So most of this work is funded under a California Energy Commission research project. And the primary focus of that specific research project is to demonstrate new types of heat pump equipment that use refrigerants that have an ultra-low global warming potential. And the idea is to apply these types of machines in existing buildings where we can dramatically reduce the natural gas consumption or the fossil fuel consumption of the space heating system primarily. In some of those cases, the projects are looking to fully electrify those buildings. In others, they're getting 50, 80%, 90% of the way there. Now, this is a pretty big project involving match funding from Kaiser Permanente and CBE. There's a large scope, lots of different items, including simulation work and demonstration projects where we're going in and putting in one of these machines in a Kaiser Permanente hospital. But there's lots of other elements too. And the main ones that we're going to be talking about today are a new web tool that we're launching at this meeting, I guess, and 2 case studies. One is an all-electric new construction hospital, and a case study of an existing office building and related data analysis. Let me kick it off with the first resource here. And this was developed by Taylor Engineering and CBE in collaboration. What we've done is generated a spreadsheet that is available to the public that contains a list of all of the equipment that you would use for heating and cooling in kind of large building applications. And the thing that all these pieces of equipment have in common is that they all use either low or ultra low refrigerants or come with that as a potential option. And the idea here was to kind of gather together the key characteristics of all of these types of equipment in one place so that engineers could quickly and easily see what's available on the market today. As of when we launched it, we had 12 water-to-water heat pumps, or basically heat recovery chillers, from 7 different manufacturers, and 15 air-to-water heat pumps from about 9 manufacturers. And those also include 2- and 4-pipe machines that have different types of heat recovery capabilities, as well as a new kind of classification scheme for clarifying exactly how each unit is doing heat recovery, because that can matter a lot in how you actually design these systems and how they subsequently operate. So the idea here is we'll update this throughout the project. So as new pieces of equipment come on the market, or we learn about new pieces of equipment that we missed. So if you see something that's not on there or have some data to share with us, please let us know, and we'll update the list throughout the project and try and consolidate that information. So yeah, please do reach out if there's something on there that we're missing or that you know about. Now, before I hand it over to the 3 folks who are leading the elements that I mentioned earlier, I want to highlight that we also have a new project funded by the California Air Resources Board. And this project should be starting in mid next year. And the idea here is to go out and do really in-depth site visits and case studies of existing building decarbonization projects. So we're looking to do 15 in-depth case studies. That will include projects that are either in construction or in design over the next 2 years. So projects you might be working on right now if you're a designer, as well as some of those that were assessed but that the owner didn't proceed with for whatever reason. We really want to understand what are the drivers for success, what are the kind of barriers that were insurmountable in that particular case, so that policymakers can really target these decarbonization policies and strategies to make sure that we're achieving the goals that we have as a state. So this project, as I mentioned, starts in mid-2026 and is a collaboration with UC Davis with some match funding from CBE. So if you're working on electrification retrofit right now, please let us know. We'd love to hear more about it and extend that info. And with that, we have these 3 case studies. First, we'll have Jiwon, who's going to give an in-depth case study of an all-electric hospital. That's a new construction hospital that's been in operation just over a year here in the San Francisco Bay Area. And then Quinn will give you an overview of an electrification retrofit map that we have updated with over 100 projects, as well as a case study of an existing building retrofit. And then Toby will take us all home for the evening with a new web tool that we're launching for assessing the impact of different types of equipment on decarbonizing heating and cooling loads in large buildings. So with that, I'll hand it over to Jiwon. Oh, and we'll be taking questions as a group at the end.
Hi, I'm Jiwon, and today I'm going to share a case study on an all-electric medical building. Our main objective is to understand the real-world performance of heat recovery chiller paired with exhaust air coils. So to do this, we conduct data collection and data analysis on a year of hourly data. So our case study building is the UCSF Bayfront Medical Building located in San Francisco. It's a 5-story outpatient hospital and it's built in 2024. What made this building special is its all-electric HVAC design. Conventional large buildings often uses chiller paired with cooling tower for cooling and natural gas-fired boiler for heating. As you all know, natural gas-fired boiler creates large carbon emissions, and cooling towers consume a large amount of water. Heat recovery chillers can address this challenge by capturing the waste heat from cooling and reusing this waste heat for heating. But in practice, buildings' cooling demand and the heating demand is not perfectly matched in real time. So, since the heat recovery chillers runs to meet the higher demand, there is excess energy in the lower demand side. To manage this imbalance, our case study building uses exhaust air coil. These coils reject or recover excess heat through the exhaust air stream. So it is especially effective for buildings with high ventilation requirements. On a cold day, heating demand is high while cooling demand is low. Heat recovery chillers run to meet the high heating demand, and excess cooling chilled water is supplied to exhaust air coil to cool down the exhaust air. On a hot day, the situation is reversed. So we have higher cooling demand, so the excess hot water is supplied to exhaust air to heat the exhaust air. So let's see how this exhaust air coil load behaves with our measured data. This graph illustrates the relationship between outdoor air temperature and the exhaust air coil load. The blue dots indicate exhaust air coil load under heat recovery mode when the air is cooled, and the red dots indicate exhaust air coil load under heat rejection mode when the exhaust air is heated. And the coil switches between 2 modes around at 55 degrees Fahrenheit. And the coil load increases as the outdoor air condition become either hotter or colder. This heat map illustrates how much the chilled water and hot water generated by the heat recovery chiller was directed to the exhaust air coil. During the summer, from July to October, there is a large amount of excess heat is rejected through the exhaust air coil. So this means that if we could repurpose this excess heat, then we can save more energy. And for the rest of the season, there is frequent mode switching, indicating that thermal energy storage has potential benefit to increase the system efficiency. So let's go over the key takeaways. The first, energy efficiency. The system achieved high coefficient of performance. This bar chart illustrates the annual distribution of simultaneous heating and cooling COP. To calculate this, we use the pure building's cooling and heating demand, excluding the excess air coil load, since that energy isn't usefully utilized. The building's energy use intensity is much lower than the median value for similar building in same climate zone. Second, water efficiency. Since this system operates without cooling tower, the water is only used for the domestic purpose. It resulted in 65% annual building water consumption reduction, savings $130,000 a year compared to a conventional HVAC design. So as the next step, we'll be presenting more detailed version of case study at the ASHRAE Winter Conference, and the full paper is already available in our partner portal. And also, ASHRAE Golden Gate chapter is preparing for a building tour of this building in January. That's all from me today. I'll hand it over to Quinn. Thank you very much.
Okay, thanks, Jiwon. So my name is Quinn. I've been expanding and updating CBE's electrification retrofit map. So this was first created back in 2022 with around 45 projects. The idea was that I would come back 3 years later and see, with all the discussion about decarbonization and electrification, how is that actually bearing out in existing buildings? So this is what the map looked like back in 2022. This is what it looks like as of today. So we added around 100 new projects for a new total of 132. So it now represents 50 million square feet of retrofitted floor area. And we've really tried to build a diverse data set. So you can see we have a whole bunch of different existing systems and a whole bunch of new electric systems, and almost every combination of the two retrofitted. And we also put a big focus on geographic diversity. And so we've ended up so far with 39 states and Canadian territories represented on our map. Now, that's not all of them. So I want to call your attention to the fact that there's still 14 states where we don't have any electrification retrofits. If you are working on electrification retrofit in one of these states, we don't have it yet. So come talk to me today and we can get it on the map. I know most of you also do your work in California, so I want to call attention to our California problem. We've done a really great job filling out the Bay Area where we are. We have 22 projects there and counting. We have 9 south of the Bay Area where 30 million people live. So if you're doing a retrofit in Southern California, we probably don't have that either. So come talk to me. Something we noticed going through all of these projects is that there's a lot of really great descriptions of what the existing building was like, what new system was installed, but people usually don't have the time to go back and actually look at how it's performing. So we got the chance to do that with one project. This is a small office building in Oakland, 14,000 square feet. It's around 100 years old. They did do a LEED Platinum renovation back in 2007, and last year they decided to go all electric. It's an owner-occupied building, and so they had a packaged rooftop unit system that was using natural gas heating, and they converted that to heat pump rooftop units. They also converted their domestic hot water, which is a pretty small amount of their building load, and they had some rooftop solar, both pre and post retrofit, that was cutting down on some of their energy usage. So the results were pretty interesting. When we compared the natural gas energy that they were using for heating in the conventional system to the added electricity use in the heat pump system, weather normalized, we ended up seeing a 17% reduction in energy use, which is good, but not quite what we expected. Switching from combustion to a heat pump can be up to a 3 times efficiency increase. Digging a little deeper and talking to the owner and engineer, we understood that in the first winter of this system, which is what the case study was based on, they had some issues with the electric resistance tripping more often than expected. It's in Oakland, so it shouldn't really be very cold too often. That's something they've been working through. There's some immediate potential for these results to improve even more in this coming winter, so that'll be something to keep an eye on. And when you look at it in terms of emissions, which is reflected on this figure, it ends up being a 28% increase in emissions for the 2025 grid for the new heat pump system. So that was a little surprising, and the reason for that is because almost all of this extra electricity use is happening in December, January, and February. These are the months where the California grid is still not super heavy on renewables. It's when the days are shorter too. There's less solar, and that's when they're using more energy. So we were working with monthly utility data, so we applied monthly average marginal emission factors here. So we were able to account for that grid variability, but not quite down to an hourly level. However, luckily, the heat pump system is going to be in the building more than just 1 year. And when you look at it over a 15-year time span, things look a little better. So that's this. That conventional system is just going to keep combusting the same amount of natural gas for 15 years, whereas this heat pump system is going to get more efficient emissions-wise with the grid. So you can see that change. In over 15 years, that's a 55% reduction in carbon emissions. So things look better. And this is just real emissions that the building would use in its demand from the grid. This also doesn't include some like accounting benefits that you could consider, like the fact that in the East Bay, our community choice aggregator purchases about 2.5 times as much renewable energy as PG&E's basic plan. So there's a lot of factors to kind of consider here. And I think the big takeaway for me was just that it really matters when you're using this new electricity, when you're electrifying buildings, and it has a big impact on emissions, especially at the winter and at night. It still has a really high emissions penalty, even in California. You can see this reflected in the figure here, which just plots the long-range marginal emission factors that I used for this analysis. You see 2025 is still up there, especially in the winter months. The grid is still pretty dirty. It's actually higher than natural gas per megawatt hour in all months except one. Now, luckily, heat pumps are more efficient, as I mentioned earlier. So that doesn't mean that an electric system is going to always have more emissions than natural gas. But it does highlight the need for these case studies and understanding how the system you're installing is operating to make sure you're getting those savings. And luckily, as time goes on, it's going to be a little better. The grid is going to keep getting cleaner according to projections. So it's a problem on its way to a solution. This map's available now on our website. You can check it out. Again, talk to me today if you have projects to add. And we're going to summarize the map and the case studies in an ACEEE conference paper next year. So thank you. I'm going to hand it off to Toby to talk about the new Decarb web tool.
Yeah, hello everyone. I'm Toby. I'm a postdoc at CBE, and I have the honor to be the very last talker today. Nonetheless, I have a little treat for you. So I'm going to be talking about the new tool that we are developing. So you might ask yourself, why another tool? We already have so many. What we realized, and I think what most of you are aware of, is that HVAC decarbonization is a complex issue, and it's very uncertain. So many of the methods that you guys here in the room are using are kind of fragmented and inconsistent. So what we thought is, we would aim to develop a simplified web tool for early design stages that helps in building decarbonization process. And we wanted to provide you guys with the capability to compare multiple equipment types for different emission scenarios, so different locations, different years, and so on. Before I go into the details, I want to give you a brief overview of the calculations that we used and the assumptions that we made. So what we are doing with this tool is taking building loads, so heating and cooling, and also equipment, and calculate the site energy, so electricity and gas. And as a next step, we then take that information or the results for that calculation to compute source emissions using different settings for grid emissions. So that's kind of the high-level overview, and we use this kind of structure for the tool as well, and these will form the tabs in the later practice tool. So starting with the heating and cooling loads, the first thing that you guys can do is pick a location, because that sets a very important context for your calculation. So things like the ASHRAE climate zone or the GAA grid region. Next, you can pick from soon-to-be very comprehensive load library. So far, we only have pre-simulated data in there for 3 different building types and 2 vintages. But what we also want to include is measured data from real buildings, and also the capability to upload your own load data, which will make it very flexible to use. When you're done with your heating and cooling loads, you can then take it to the next step and think about equipment scenarios. What that means is that you can pick from an equipment library that we are still developing, and pick a piece of equipment for the 4 different types that I've listed in this graphic up there. What these different types of equipment form is then an equipment scenario. You can put together up to 5 of these equipment scenarios that you can use for your calculation. So in practice, it looks like this. So you have this little window where you can specify your equipment. So that means 1 piece of equipment for all these types that I showed earlier. And then there's also, for some of the equipment types, a few more settings, like for example, if you want to use the air water heat pump also for cooling. And when you're happy with your settings, you can then save it as a scenario and use it for your calculation. And as I said earlier, you can define up to 5 equipment scenarios. So when you're happy with your equipment scenarios, you can take it 1 step further and go to the emissions or grid emission settings. So this works in a very similar way. We have different settings like the grid year, the emission type, and what these form are what we call emission scenarios. And it works in a very similar way. You can modify a few settings to your liking. You can pick the grid year. You can enter the annual refrigerant leakage. And when you're happy with your settings, you can save it as one of 3 scenarios, which then sets you up for the calculation. And you see this little black button at the bottom. As soon as you hit that, it will calculate your results. Then what we're doing as a last step is providing you with a very comprehensive analysis and results tab. So for now, we've included 5 different types of graphics, starting from a stacked bar chart showing emissions, going over to bar charts for energy and emissions. So all of these charts are very interactive, so you can filter for certain equipment scenarios that you're interested in. You can also filter for emission scenarios. You see an interactive hover tip. When you hover over your bars, you get more contextual information. And now I want to move on to this time series, and you can see that in action. So there's filters at the top. So in this case, you can pick your equipment scenario. That will then change your graphic. You can also change the type of visualization from a stack graphic to a simple line plot. Or even if you want to aggregate it in a different way, you can go from weekly to a daily visualization. So it's very, very flexible, and that was one of our main goals. We also included a heat map, which is super valuable if you want to look into hourly results, which can be pretty efficient for emissions. But you could, in a similar way, also visualize electricity use. And then as a last plot, and again, there's a little animation in here, there's also a scatter plot, which might be very helpful if you want to correlate your emissions against outdoor temperature values, for example. But again, we set it up in a very flexible way so that you can change both the variables on the x-axis and y-axis. So this is just a very brief overview. We launched it yesterday, so it's an alpha version. There are lots of bugs, but still we wanted to put it out there to get your feedback. Because yeah, that's obviously very important for us, and we really want to take your feedback and develop this tool further. So a few of examples that we want to, or features that we want to include is expand the building load and HVAC equipment libraries to make it even more flexible and valuable to all of you. Add new data points like utility costs, embodied carbon, water use, etc. We also want to enhance the visualization and reporting capabilities and make it more flexible so you can use it directly in your reports. And overall, we need to spend more time on documentation and make it more usable for you. So by doing all that, we hope that by the next CB meeting in spring 26, that we will be able to launch a public beta version that's not only available to you guys. Saying that, the alpha version of the tool is in the partner portal, so you can log in, there's a link, and you can check it out already. Again, it's an alpha version, but still we are very keen for you to test it. So I'm the last presenter. If you have any questions, I think the other guys will come on stage now. There's also a breakout session on building decarbonization with Paul later on, and there's a QR code that brings you to the CBE project page.